It's gonna be very down-to-earth, practical presentation. I know writing code is not super popular nowadays, but my hope is that maybe you can give all that to an agent and it makes a better job at writing Aiken code at the end. So, optimizing Aiken programs, because I guess I got annoyed hearing people that Aiken is not optimized. You can actually write good Aiken code, so the problem maybe is just between the chair and the keyboard. Or actually, well, it would be more fair to say I'm sorry to not have made the compiler better. But yeah, most of those things I would hope they were in the compiler. They might end up in the compiler at the end of the day. I mean, one day, sorry. But for now, there's still stuff you're gonna have to do yourself. Before we start, small preliminaries. Always before you start measuring anything, have benchmarks in place. Before you start optimizing anything, have benchmarks in place. There is no point benchmarking anything, optimizing anything if you don't measure what you're actually optimizing for. And Aiken make that relatively easy because all the tests in Aiken have automatically CPU and memory units that come with them. So it's fairly easy to just measure the execution cost of a program. And for this type of thing, I will always prefer using end-to-end benchmarks, which means testing the validators directly, which is also made possible relatively easily because validators are just functions, so you can just call them, pass them the context, so that the transactions, the redeemers, and whatever they need for that particular purpose, and just look at how your validator perform. Now, to really measure what you want to measure, it's important also to separate the fixture, so the code that serves at preparing the data for the test, from the test itself. And that's because you don't want to be measuring the construction of the transaction, since this technically happen off-chain, not on-chain. And you can use constant for that in Aiken. So for those that still don't know, constant, they are evaluated during compilation, reduced to their minimal form, so that then you can just apply them directly. They get in line in the places you use them, and so they bear no cost, basically. So you can have arbitrarily complex computations as constants, and then put them in your tests, so that what you end up measuring in the test is really just what's actually going to be executed when you run that validator. Now, one step back. A typical way to write transactions, because that's usually the interesting bits, is to use this little transaction placeholder that's coming from the standard library, and that creates just an empty transaction that has nothing, or placeholder values for pretty much everything that's in the transaction. And then you can, using the record update syntax, stuff in the things you want to add for your smart contract. Now, how would you typically do that? Stuffing all the little values, using fuzzers. Fuzzers provide a good way to generate arbitrary values for literally anything that you can find in the standard lib. So that includes all the different pieces of a transaction. And fuzzers always come in two forms. One form which is very much arbitrary, give me one output reference, and one form where you can specify an output reference with some constraints, if needs be. So in this example, I'm generating an totally arbitrary input, but it has just a min ADA value as a value, no datum, no reference script. And that still gives me not an input, it gives me a fuzzer of an input, which means it gives me a way to generate input given some random seed, which is typically what we would give the property test engine in Aiken to generate inputs. But it's also very possible to just call the fuzzer manually using a static seed to get just sampled inputs if needs be. So that's the generate function. That's how you would write it. You don't really have to write it yourself because it's just provided in the fuzzer library already. So the general idea being you can write generic fuzzers. If you need a particular input for a particular test case, pass it a label. The label is used as a seed so that if you pass in the same label, you get exactly the same input. And if you want a different input, you pass a different label. Okay, so far? So that's just really how to get to write those benchmarks before starting optimizing anything. Now, the standard lib. There is some debate about whether or not you should use a standard lib because, well, a standard lib is quite opinionated in the way it's written. And it is reasonably optimized in the sense that there are some good tricks in the standard lib and it's trying to do things properly. But it's also tuned for correctness. And the standard lib in particular is meant for avoiding yourself, shooting yourself in the foot. So sometimes it's a bit more generic than it could be. Sometimes it's a bit more focused on the error handling than it could be. And it's kind of up to you to decide where you want to stick to the standard lib and when you might want to deviate from it and simply what I call surgically replace functions in your smart contract. The whole point of the standard lib is that it's easy to audit, easy to use, it's safe to use, and if at some point you think, I don't need all that genericity or I don't need all that safety, well, you can simply inline the functions you need in your validator and replace it. Having said that, there are a couple of functions in the standard lib that you probably never want to use in a validator. They are good for testing. They are a convenient way of writing your tests, of writing code that's surrounding a validator, but probably not a validator. And that's like more or less an exhaustive list. If you see any of that in your production code, there is probably a problem and you should probably be doing things differently. So I will probably turn those slides eventually into some page on the Aiken website so that all that knowledge can be found again. So now, optimizations. We're gonna go from some simple stuff to a bit more advanced esoteric stuff at the end. I'm sorry at the end of the day, so it might be a bit tricky to follow sometimes. Do not hesitate to interrupt and ask questions to clarify a piece of code if needs be. But the first trick, it's not really a trick, sounds a bit stupid when said like that, but use simple structures. The whole idea of Aiken revolves around the fact that all the types are not really encoded actually, they are just manipulating serialized data, which comes at some benefits that you don't have to deserialize data, and you can directly operate on that. But that means that if you are constructing values in Aiken, you're paying the cost of serializing data every time, deserializing it when you want to use it. And most of the time, you're actually better off passing parameters to functions than trying to create intermediate data that you pass to functions, because then you pay the cost of creating that intermediate value, pay the cost of passing it, and pay the cost of deserializing it every time. So the types, I would say, mostly exist for interoperability with the outside world. That means your datums, your redeemers, and outside of those two contexts, you probably don't want to use types, but limit the amount of types you use. And there is, in particular, one type you almost never want to use as is, or to construct yourself, it's value. A value is complex. It's a nested dictionary that contains many things, and the vast majority of the time, you actually just want to work with dictionaries or with pairs directly if you can. So avoid using value unless you really have to, because you are into the properties that the value gives you, which is that it cannot contain an asset with a zero quantity in it. If you don't need that invariant, you probably don't need value at all. Second, I would say design principle, and that's something you have to do in Aiken, fail fast. Which sometimes it feels a bit counterintuitive because as developers, we sometimes want to handle error and make sure that things are smooth for the users. Smart contracts is not the place for that. It's the place where you have to be brutal. If something does not abide by the spec and by what you expected, you fail loudly. There is no point trying to recover from errors if something is slightly specified wrong. That's not the place. You're just gonna lose execution units, and you almost never want to do that. Again, unless you really have a reason to do it. Just a small note here, in case people don't read changelogs. Since a few releases now, you can pass triple comments on top of expect in Aiken to actually create a trace at runtime in the compiler. And so that's something that was requested some long time ago. And now you can just do that. So those two things are not equivalent, but yeah. Then, a bit more subtle now, avoid unnecessary pattern matches. And there are many scenarios actually where you might want to write something like that. Like you want to check if an element is in the list. And the typical way of writing that is you're gonna iterate over that list. If it's empty, well, the element is not there. And otherwise you take the head. The element is either the head or you're gonna look into the tail. And eventually you end up writing something like that because you want to fail fast. So you say, well, I'm expect the element to be there. If it's not there, blow up. Thing is, now on every single step, you're actually pattern matching to see if the list is empty. And if it's empty, you're gonna have some behavior. If it's not, you're gonna do something else. But if you really expect the element to be there, you don't really care to check if the list is empty. So you can just write an equivalent function that just take the head of the list. If the list is empty because you've hit the end of the list, well, the element was not there. So the whole thing will blow up, and that's exactly what you want. And if it's there, well, the OR condition will actually never execute the other part because it's lazily evaluating both operands. And so you save quite a lot of execution units doing that. So every time you have what I call an infallible search, and you do expect to find something in the list, you can simply short circuit and use unsafe operation. There is no need to pattern match every time to make sure that the list is not empty. A bit of a similar one. There are many scenarios where you do know the length of a list ahead of time. And that's, for example, the case where you're gonna iterate over inputs. And here, maybe you don't want to be failing if the inputs is if you've hit the empty list, because what you want is accumulating all the tokens inside the inputs. And the typical way you would write that is, let's accumulate all tokens, iterate on every input until it's empty, and when it's empty, I return my accumulator. Now, the inputs list, you know it when you construct a transaction, so you might as well pass the length of the list as a redeemer. And instead of checking if the list is empty, which is an expensive, with quotes, pattern match, you can simply check an integer comparison, which is actually much faster. And as soon as you've hit the end of the list, now you can return the accumulator. Plus, and it's very crucial, you have to check that the list is actually empty. Because otherwise that means you're opening up attack vectors where someone could be providing purposely a wrong list as a redeemer to try to make you skip some validations. So this goes a bit in the spirit that your validator should limit the amount of computation it does, but should always validate the expectations. And here the expectation is that the length that was provided was the actual length of the list. So it's a tiny check, happens once at the end. And the whole thing is actually much more efficient than trying to pattern match on the input list every time, especially when the input list is 300, 400 elements. Slightly more subtle, this one, but in the same way that pattern matching can be costly when you repeatedly do it, it is also interesting to limit the amount of conditions you evaluate at once, especially in recursive functions. So to give a concrete example, here I have an case where I pull a integer value between 0 and 255, and I want to use that to choose an action uniformly between 4 different paths, right? So if it's lower than 64, do one, lower than 128, do the others, etc. Now, that means on average, if we assume that I is uniformly distributed, you're gonna do 2.5 evaluations. So n plus 1 divided by 2, n being the number of branches you have. Now if you reshuffle a bit the conditions so that you do a binary search, and first you're gonna split the set between 2. So everything that's below 128, everything's above, and then you separate the 2 remaining cases. You end up doing only 2 evaluations all the time. And that has 2 benefits. It makes the fees more predictable, because instead of being sometimes 4, sometimes 3, sometimes 1 evaluation, it's always 2. And the number of evaluation you do is in logarithmic size of the number of conditions that you have, which starts already being better at 3 conditions, but start matters to matter even more when you have 10, 15, 20 conditions where I kind of sometimes could see. And that is not really...
Unless you expect the values to mostly be under 64?
Yes, yes. So that's the next slide. So of course this is, I mean, all those tricks always, it's to not to be applying blindly, but need to think about the use case you're applying them. And here, it's in the case where I is uniformly distributed. Precisely. That means even if you don't have a case like that, you always want to be thinking about which conditions you want to be evaluating first. Because that matters, since or and for that matter, I mean, or here would be lazily evaluating first operand and only evaluate the second if the first one is false. So in case you have a check that is very frequent and very cheap, you want to put it first, so that you never have to evaluate the second one. And here is just a stupid example I found at some point, but in practice, it's just something you do on a case-by-case analysis and think, oh, actually, which one does occur most often? Which one do I want to always evaluate? And which one do I want to defer as much as possible? Similar one, again on the conditions. And that's an example I picked from the standard lib, actually, in the function that is inserting an element in the dictionary. What we typically do in a recursive fashion, we look at every element in the dictionary and we try to check if the key we're trying to insert is the same as the key we are iterating on. If it's the case, we've hit a terminal case and we can just replace the key at that element. If the key we're trying to insert is smaller than the key we're just seeing, well, that means there is no need to go further in the dictionary because it's order in ascending keys. We can just insert it before. Otherwise, we just loop. Now, if you do that naively like that, on every single iterations, you're gonna evaluate two terminal conditions. You're gonna check if the key is equal, if not, if the key is smaller, and then loop. If you now change that a bit to say, well, I'm gonna check if it's a terminal case, and if it's a terminal case, now I'm gonna check for which one it is. On every iteration now, you only evaluate one condition, and you only need to pay one extra evaluation once you've found the actual place you need to insert the element. And that's something which applies actually way more than you would expect. But every time you have two terminal cases like that, or multiple terminal cases, and you are iterating over something, you probably want to lower the amount of work you do per iterations and simply defer as much as possible the checks you need to do so that they only happen once. Silence. Okay, another one which is really playing into Aiken core features here about data equalities. One of the main reasons Aiken was built the way it's built is because checking for data equality in Plutus is extremely cheap. Relatively cheap. At least the most interesting part is the constant. The memory evaluation, which is constant, always, cost 1, which basically means nothing because they couldn't put 0, so they just put 1, which is the minimal value. And that's insanely cheap. That means there is no memory cost at all in comparing two values. And the CPU cost is also fairly cheap. You pay kind of an upfront cost of almost 1 million CPU units. And then you pay per the size of the data that you are comparing, where X here is kind of subtle to compute, but relatively small in practice for most of the value you would ever encounter. And a good example of that is the asset.match function from the standard lib. That's kind of meant to compare two values, but allow you to pass the second value as just a plain data, where typical use case for that is when you store that value in a datum and you want to make sure that the value you're storing matches a value you've computed in your validator. That is doing a very efficient equality based on that fact. But the gist really being that if you can compare data, you probably want to do that instead of manually unpacking and deserializing objects into smaller chunks that you can then compare individually. And to give a concrete example from one of the recent code bases I've been working on, we had to compare the an input and a continuing output in the context of the programmable tokens when there is a seizure of a token from a third party. So you want to make sure that the UTXO that gets seized is exactly the same in the output as found in the input, minus the tokens that have been seized. And so the way we do that is, well, we look at the UTXO that's being seized, and we split it at the policy being actually seized. Everything before is reconstructed rapidly as a small list, and everything after is just left untouched. It's a plain data object. And then we can simply compare that the part before matches, the part after matches, and the part that we are actually seizing is different. And then we can perform additional checks on that to make sure that the tokens that have been seized goes on the right place. But really the important bit here is that we don't compare the inputs or tokens before and after one by one manually. We simply do a big data equality because that is saving a lot of execution units. Okay, another one which kind of became a thing as a consequence of something else, let's say. So we had introduced backpassing at some point to simplify the syntax. And for those not familiar with backpassing, it's a syntax that allows to, get functions that take a callback as a last argument and sort of move the callback to the front of the function so that we can unnest the code instead of having to pass a callback to a function. What you can do instead is put the argument to the front as if they were let bindings, and then have everything else that follows be the body of that callback. What this allows in practice is writing in what we call a continuation passing style, which has the nice benefits of completely avoiding to create tuples as intermediate arguments when we have to return multiple values from a function. So in this example, on the top, we have a function which will typically return in this way. It takes 2 arguments and returns some triple. And we pay a cost here twice when we create the triple at the end for returning, and when we pattern match on it after calling the function. Now, if instead we move that return value as a function, a callback that would take this as an argument, we can simply use the backpassing syntax to, almost transparently change that and get back our 3 results without having to create the tuples anywhere. And that is very easy to do nowadays with backpassing, and saves over many cases quite a lot of execution units as well. This is in particular very useful in functions that are recursive and that need to return multiple results. For example, you're folding over some lists, and you need to both consume some proofs maybe and accumulate a resulting value at the same time. So it's quite, it's so common that we ended up having 2 functions in the standard lib, fold L2 and fold R2, that are following these patterns. And once you have it for 2 elements, it's very easy to generalize to 3, 4, 5, 6 if needs be. If you really can't use backpassing for some reason and you still need to return multiple values from a function, it is better to use pair, which is a built-in type that we have in Plutus, specifically meant to pair 2 elements, because it is generally better than to use tuples. The only case where it's not better is if you are only accessing the first element of the pair. But if you are only accessing the first element of the pair, why are you returning 2 elements? Right, just return the first one. So most of the time you do want to use pair, and they also play nice with maps and with values and dictionaries and so on. So usually you almost never want to have 2 tuples. The only disadvantage of using pair is maybe the syntax is a bit, a bit more letters to types, but nowadays we don't type code anymore, so who cares? Probably the most important optimizations actually on the slides. Avoid traversing the same structure multiple times. That's stuff like that I see very often in code because it's kind of convenient. It follows intuitively the way we think, But when you think about it, we're like, okay, count all the inputs according to some predicates, and then, well, give me a filtered list of the same inputs, again, according to some other predicates. And so now if I have 300 inputs, I've traversed that list of 300 inputs twice and paid the cost of traversing that list twice, which is likely the most important cost in these two functions. So what I can do instead is use something like FORDEL2, where I just say, I'm going to traverse the list of input once and accumulate the two things I'm interested in one go. And yeah, that is the most important optimizations, because that's usually where you're going to save most of your execution cost. If you spot a place where you are traversing inputs or outputs multiple times, there's probably something to be done. Another example of this nature, let's filter all the outputs, and then let's apply some condition on the outputs I filtered. This is not great, because now you're traversing once the structure, creating an intermediate structure, and then retraverse that structure to do some predicate that you could have just done to begin with on the first traversal. So the way I kind of like to think of it is, when you validate a transactions, you're gonna kind of look at all the inputs, look at all the outputs, and you only need to look at them once because they're not changing as you validate, right? So as you should gather all the information you can at once, and only visit all the parts of the transaction once. Except...
A quick question. Sorry.
Yes.
Yeah. Are there any plans to add list fusion to Aiken?
No. So, no, as I said at the beginning, I wish most of those slides did not exist, because I wish that these were things you don't have to think about as a developer and that the compiler does for you. But, well, priorities is not elsewhere. So the compiler is not probably addressing that unless someone is very motivated. I'm always happy to onboard someone on the code base and see what we can do. But yeah, no. I was saying, yes, so don't traverse inputs multiple times or collection multiple times, except in cases where you really have to. And concrete example could be, you are validating inputs and outputs, or all outputs, and you need to check that the payment credentials corresponds to some withdrawals that is part of your withdrawals. And you don't know where it's going to be in the withdrawals. So you have no choice to be retraversing the withdrawal list constantly to check for that trip hash. And that means now you're going to pay the cost of traversing the withdrawal list for every single input, or every single validation that you do. So here it can be worth to build a cache or a simpler structure than the one you're going to need to traverse multiple times, where you would pay a one-time cost for building that cache, but usually that cost will then be completely erased by the fact that then accessing the values you want is a lot simpler. And in this example here, I'm just using function composition, which really is that I'm replacing more or less every pair in the withdrawal by a function that check against that particular value. And the reason that works well is because behind the scene, Plutus is a lambda calculus, does well with function, better than with linked list. So you are better just executing a chain of function compositions than traversing a serialized list of values. And in this particular example, if you are in the case where you only have a single withdrawal, that particular optimization is going to be worse, because the cost of creating the cache usually will not be worth. But as soon as you start having 2, 3, 4 withdrawals, then the cache starts to pay off. Okay, a bit more deep. Unrolling recursions. That is something which sounds scary when you just look at the title. But what it really means is there are many scenarios where you can do multiple steps at once instead of having to do them step by step. Typical example would be you're trying to pull an element out of a list. The way you would typically write that is, well, you pass in the index of the elements you want, the position you want, the list. If your index is, well, technically equals to 0, but let's go with that smaller or equal, then you get the head of the list. Otherwise, you're going to look at the tail of the list and decrease your index until you find it, or until you don't. Now, if you have a very long list, you might try to check if the index is large enough that you can maybe do 2 steps at once. And if your index is greater than 2, you know that it's not in the next element. You know that it's not in the one after. So you might as well just unpeel both elements at once. And if you do that, like finding an element, let's say in a list of 100 elements, and you want the element at position 80, on the first case, you're going to have to do 81 steps. And on the second case, you divide that by 2, basically. Because on every iteration, you are converging twice as fast. And here, I've used 2, but you could use also 3, 4, 5, 6, depending on how, the knowledge of your list and the knowledge of your domain. And that's always why it's important to pair those optimizations with what you're actually optimizing for. But in that example, that's almost as costly as the implementation above and will almost always be better. So that's almost a no-brainer to just go with that instead of the above. And some of those things are already done in the standard lib in this way, but you can also just do these kind of things as you, in your own code. Another one that's kind of I've learned along the years.
Sorry, I have questions here. About the last slide, I was wondering about the cost of the second algorithm.
The cost of the second one?
Yeah. Because I'm seeing like the first one is a scala conquer. I was wondering if the first algorithm is has less cost than the second one.
Yeah.
Okay.
In almost all scenarios, it would have less costs.
Oh, I see.
Because you're avoiding doing as many recursions. And every time you have to do a recursions, you have to do a function call, which means you have to put some context on top of a context stack, and the VM has to unpeel that and then execute the next functions. So you pay really the cost of like rerunning the functions. Whereas here you're kind of, short-circuiting all that to just do multiple steps at once.
Thank you.
I don't know the support, but wouldn't it be better in the previous slide, or wouldn't it be good to just reconvert that to tail recursion and then you avoid some of the calls?
That's coming. But before that, byte arrays, they are extremely efficient on Bluetooth. So much efficient that it almost sometimes makes you just want to use byte array everywhere. It obviously impairs readability. It can make things a bit tricky to follow, but in many scenarios, for example, where you would have a structure type that takes 2 byte array, and then you unstructure, you destructure that type to get the keys and signatures, you would also be just better off passing a single byte array and then slicing into it, because that is a lot faster than the above. Yes.
Is that just like kind of a hacky way to introduce an array type into Plutus?
Yes.
Would it be better to just have an array type in Plutus?
Only if the ledger could provide the array in the script context.
Sure, it can.
Last time you said no.
Well, Plutus needs to have a representation,
Yeah.
right? And then we can convert it. That's not a problem.
Yeah, I wish we killed the data type and we had just better primitives across the board for arrays, for hash maps, for byte arrays. But yeah.
Agree on the previous. Funny thing is that we are going to have the arrays kind of very soon in next hard fork, but surprisingly, the built-in operations on this array have such cost that it's cheaper to use list operations up to a certain point, 7 elements, I think, which is insane. I don't know. I really find it really ironic that the best way to validate, to write a validator, efficient validator, is to use imperative style, and we use immutable functional programming language for that.
Yeah, I think we should have a whole session on why we should maybe adjust the next hard fork, but that would be for later. The gist really being that byte arrays are great. in Plutus. They are fast. They have nice primitives. You can mostly do whatever you want with them. And for example, you can also use them as registries for cache as well. It's a stupid example here, but at some point I was trying to micro-optimize stuff that shouldn't be micro-optimized. But for example, I had a code which was doing modulo 2, and was doing it very often in a recursive manner. And turns out it's actually better to just look up the value in a byte array that you have pre-computed. And in my case, I knew x was never going to be greater than 255, so I could just create an array of that length and do a byte array.add with my pre-computed value. I pay the cost of storing that byte array in my program, which can be a few bytes, but that is almost 2 to 3 times more efficient than actually computing the modulo, which is stupid. And another example we have in the standard lib, actually, you need to calculate the power of 2. And what it does actually is like the first values, we don't calculate them, we just look them up in an array. And then we use this, unrolling recursions as well quite heavily. So that function looks probably a lot different than what you would imagine it to look like. But that is quite efficient in the end. Yes?
You mentioned that operating with byte arrays or lower data types is faster, but it comes at the cost of readability.
Yes.
In several languages, when you wrap, you make multiple function calls, those get optimized and doesn't cost the function call. Is it the case in Aiken? Could I wrap the less readable functions with more readable ones?
Yes. So Aiken has one particular optimization that's useful, which is that if you have a function that just wrap another function directly by maybe swapping the arguments or doing something like that, it's as if the outer function never existed, right? It would always unpack it completely. So it's completely comes at no cost. And yes, you're right that it embeds readability, and that's why, maybe I did say it, I don't remember, but that's the kind of optimization I would only do if you really have to, because in the example I was showing before, it's a typical case where I would not do it, because here you are barely saving anything, or like really if you are after like thousands of execution units maybe. But a case where I would typically do that is if you have a list of those things, right? You are passing maybe a list of proofs to your contract, and I'm anticipating your talk very soon. But that's typically where, like, instead of having structured proofs, since your proof is anyway generated by some other programs and that doesn't have to be human readable, the proof might as well have its own encoding and be compact enough that you save execution units by processing a list of proofs.
Could Aiken introduce an array type that desugars to this byte array stuff?
This looks like a storable array, right?
Yes.
For example, you cannot have simulate arrays of lists, right? With this approach.
It is more tricky because here it's very handy when you have values that are just integers below 255. If you have bigger integers, you can simply combine multiple, contiguous cases in your array, right? If you have more than that, that becomes tricky. That means you need encoding, and then you're like encoding the value in an array, and it could start to be too complicated. So to answer your question, yes, we could potentially have syntactic sugar for that. Haven't thought about it. So,
and the thing is, most of the arrays you're dealing with, you're reading them from somewhere. You're reading them from a redeemer, or you're reading them from the inputs, right? Or you're reading them from, I don't know, a constant, right? Yeah. So you're never really constructing these arrays dynamically inside of the on-chain code. But if you are, probably you'd be better off providing it kind of from the redeemer and checking it.
Yeah. Correct.
If you add array as a syntactic sugar, then your script becomes bigger.
Yes.
Okay, so it's another catch-22, right?
Correct.
Like you think to be smart and to make the execution faster and cheaper, but then you're paying space, and when you call your contract is bigger, and then you end up paying more. So
so you're really playing against execution units on one side and script size on the other side. So there are scenarios where it will be better, but there are scenarios where it wouldn't, which is why, come back to the first point of the slide, always measure and always make sure that what you're doing actually improves what you're after. Now, if we take that kind of lookup concept a bit further, we have Merkle, Patricia, Forestry, which are basically key value stores of arbitrary size. If you think about it, a function is just a key value store, just with a lot of values. But if you know that your input domain, like your X, can't get really too large, maybe it can have a billion values, you could pretty much pre-compute all the possible values it can take, store that in the Merkle tree, and then provide a route to your program. And that becomes interesting as soon as the computation you have to do is more expensive than roughly 1% of your execution budget. And that's because it is basically the cost of looking up in a Merkle Patricia tree. So any expensive computation that will be beyond these limits, you might be better off just looking it up. And instead of having to compute it on chain, you simply pass the input value, the expected results, and you have a route from which you can take check membership. Now, again, leaning back into this learnings, you want to avoid computing things in a smart contract because usually, or in many scenarios, it is easier to verify if something is true than to actually compute a result. So a good example is the square root. You can compute the square root of an integer on chain. You use some kind of Babylonian algorithms to converge to that. That's great. But it's also extremely easy to verify if something is a square root of something else. You just multiply it by itself. And so in these scenarios, you would be just better off passing the actual square root as a redeemer and making sure the contract checks that, having the computation happen off-chain. But that's a principle that you can apply to many, many things, actually. Like, every time you are computing something on-chain, ask yourself, do I need that computation to happen here? Or could that computation happen somewhere else where I could just verify that the computation is correct? And in many scenarios, surprisingly, that's the case. Now we arrive at tail recursive functions. We don't have tail rec optimization in Aiken, which means that Aiken will execute recursive functions pretty much the way you write them. There are some optimizations happening, but not this one. And what is a tail recursive function is really a function that will that can compute the intermediate value as it's iterating, and doesn't need to expand fully all the different cases before reducing that into a value. And turns out in many scenarios, because of the way the Plutus VM is made, tail recursive functions performs a lot better. I think the only case where they don't really perform better is when you have an accumulator that is very simple, like just an integer, where they are basically equivalent. But in many scenarios, especially if you're accumulating over some byte array, it is almost always better to write a tail recursive version of your functions. And here it's just a stupid Fibonacci example, but the difference of the execution between these two is 10x, I think, 20x. It's really, really massive. And last, there are plenty of invariants provided implicitly by the ledger, which can be leveraged when we do validations. Examples, many things in the transaction context are ordered, and there is no way they cannot be ordered. That's a ledger failure, so that's things your smart contracts can rely on. Values are also interesting in the sense that they always start with value that are in output, and value that are in the minting policy, the minting field, they also never include ADA, which is also an invariant you can rely on. No, that's in Plutus V2. We don't do Plutus V2 anymore. So it's only a Plutus V3 talk. I mean, Aiken doesn't compile to Plutus V2 anyway, so anymore. But yeah, they are never negative in the output. They can be in the minting policy. They are also ordered by ascending policy and assets. And you have other interesting properties like the transaction is balanced, because if it's not gonna pass. So that means if you sum all the inputs, all the minted value, you're gonna get the same amount as the output and the burn value. Yes?
I have the mic.
Sorry, I saw
So
you second.
yeah. So thanks. So you say, yeah, inputs are ordered. This is nice, but it's also a liability, no? Because if you want to see whether something is spent, you need to find it in the input set. But if it were basically ordered as provided, you could actually encode more invariants, actually not only by the ledger, but actually by your application. So you would actually need to verify less on-chain because you say, if it's an important value, it must be the first input. But inputs are inherently sorted by the ledger. In outputs, for example, it's very easy to say, okay, my protocol has exactly the thing I care about always as the first output. That's a given, and you can actually optimize with it. And gives you a smaller space of what you need to verify on chain.
Yeah, and I thought at some point about including something like that in the presentation, and over time I found that to be an anti-pattern because you are forfeiting composability if you do that. Because now if every smart contract expects the first output to have some special semantic, then you end up being slightly, cornered in your own scenario. So it's usually better to put the outputs wherever you can, but simply tell the smart contract where it is, right? So you give it the index where it has to look up so that it can do a fast lookup in the inputs or outputs instead of having to kind of unpack them all.
So both of those points are affected by nested transactions, right? So first of all, the sub-transaction will not be balanced anymore.
Did I tell you how I hate this CIP or not?
However, it brings a lot of value that you haven't thought about. Like, for example, you can have a sub-transaction that just has one input that it spends, and the other one spends another input. So you can put this do this situation where you have only one output or one input that is yours, right? And you can always rely that it's yeah. And there is a SIP about this ordering, right?
So I think my point is not so much about what the invariants are, than the fact that there are invariants at any point in time,
Absolutely.
and you should rely on that and not revalidate things that are just axioms of the validations.
Absolutely.
But yeah, good point. And that's all. No, different.
Can you go to the last previous slide? Yeah, I'm seeing the second algorithm is using dynamic programming, right? And the first one is just subtract and conquer. So in the second one is like has less cost than the first one. So that's the reason why you are saying this is the first option just to do algorithm, for example, right?
No, the main reason the second one is better than the first one is that the first one, to get to a result, what the machine will do is to evaluate these functions, and in order to evaluate it, it will have to unpack it to the next level and unpack it to the next level.
Yeah,
and
exponential.
until
right?
when it has reached the end, it
Yeah.
can start combining all those values back into the results.
Yeah.
Whereas in the second case, it will calculate the intermediate result as it iterates.
Yeah.
And that means there is less context the VM has to remember, and that results in far less execution units.
Okay, thank you.